Dear students, in the today's lecture, we are going to discuss different cases of simple harmonic motion. In the previous lecture, we have discussed about what is simple harmonic motion, what is its equation of motion, and its solution. In the today's lecture, we are going to discuss different cases of simple harmonic motion. Those cases are one is free oscillations, damped oscillations, forced oscillations. What are free oscillations? What are free oscillations? A body is continue to oscillate with same amplitude for infinitely long time. Such oscillations are known as free oscillations. What is the meaning of this one? The amplitude of oscillation remains same for long time. In the nature, the situation we never observe. It is the ideal case only. I will show one demo by using animations provided by PHI learning system. See this one. Here, there is no friction of surrounding media. Then I will take this pendulum to certain position here and leave it like that. Then see here, amplitude always remains same here. How much time you spent here? The amplitude always remains same. This is possible only when there is no friction between this pendulum and surrounding media. That is not possible. Always some friction between this pendulum and surrounding media. That's why some loss of energy takes place and the amplitude continue to decrease. After certain time interval, the pendulum comes to the rest position also. That situation is known as damped oscillation. But presently what I am showing you, those are free oscillations. In this case, the friction is completely absent. That's why amplitude always remains same. But generally it is not possible here. Now I will apply some friction here. You see here. I am applying some friction here. When I apply the frictions here, the amplitude start decreases here. So after certain time interval, the object comes to the rest also. This kind of phenomenon is known as a damped oscillation here. But the concept we are going to discuss here is a free oscillation. In this case, the friction is completely absent. So in this case, resistive or damping force are completely absent. In nature, this will not happen. Free oscillations are ideal case only. The equation of motion of free oscillations is d square x by dt square plus omega square x equal to 0. This equation we have already derived in case of simple harmonic motion. In that case, we consider only restoring force. We have not considered any resistive force. That's why the simpler motion, equation motion, what I have considered, that at that time we consider only restoring force. So the same equation we can consider for free oscillations here. And here omega is the angular frequency. That value equal to root k by m. K is the restoring force constant. M is the mass of the system. Here omega is the natural frequency of that system. Omega is the natural frequency of the system. Now we are going to discuss the second case, that is damped oscillations. We already discussed in the previous discussion, when there is a friction, the amplitude decreases continuously. After certain time interval, the object becomes a rest position. That means equilibrium position. That already we discussed here. So if you want to define this one, when a body is in oscillatory motion due to resistive forces offered by the surrounding media, the amplitude decreases continuously and reaches equilibrium position in a finite interval of time. Such oscillations are known as damped oscillations. I will show one animation here. Here you see here, in this case, a spring loaded with some mass here. Now, the oscillator set in this system. So then what happened here? The initially the amplitude is this much here. Because of this friction between this surface and this object here, then what happens? There is a loss of energy occurs. See, amplitude is decreases continuously here. So there is a amplitude decrement with time, and after certain time interval, the system will comes to the equilibrium. These kind of oscillations are called damped oscillations. We can show this kind of analysis by using a animation which here I am very much thankful to Dr. Surendranath sir. He has provided this kind of animations. Students can easily understand what is this and these oscillation systems. See here, this is the system amplitude 15 units for suppose frequency is 5 hertz. Then there is no damping effect. So this damping is because of friction between surrounding media and that oscillator. But there is no damping effect. That means damping effect is completely absent for suppose. See here the system how it oscillates here. Here only restoring force. This arrow mark is observing. Na? This arrow mark tells about the restoring force. See here the amplitude remains constant. How much time it Now I will introduce some damping effect here. When I introduce this damping effect, see here how the amplitude. So amplitude is decreased. So there is a more damping effect than the fall of amplitude very fast. So very short period the system will come to the equilibrium. So this damping effect depends on the friction between the oscillator and the surrounding media. Now, in case of damped oscillations, just now we discussed here, there is a friction force exists between the oscillator and surrounding media. In addition to the restoring force. In case of free oscillations, we are having only restoring force. But in case of damped oscillations, we are having a resistive force in addition to this restoring force. Resistive force is always directly proportional to the velocity. We can express velocity as a dx by dt. The restoring force directly proportional to the velocity. The velocity we can write dx by dt. We put the negative sign because it is the opposite to the motion. That's why we put the negative sign. So now this proportionality replaced by a constant gamma that is known as a damping coefficient. What is this gamma? Damping coefficient. Then what is the total force now? The total force acting here is restoring force minus kx and resistive force minus gamma into dx by dt. So the total force is minus kx minus gamma into dx by dt. Now, according to Newton's second law, F equal to ma. So a is nothing but acceleration that can be written as d square x by dt square. So we can write F equal to ma that equal to m into d square x by dt square. Now we equate these two forces. Then m into d square x by dt square equal to minus kx minus gamma into dx by dt. So now I will take this negative terms left hand side and divide throughout with m. Then the equation becomes d square x by dt square plus gamma by m into dx by dt plus k by m into x equal to 0. So first I have taken left hand side. Then what happened? This negative becomes positive here. So these are also positive. Then divide throughout with m. So here m will be cancelled. Here gamma by m. Here k by m. So then the equation becomes d square x by dt square plus gamma by m dx by dt plus k by m into x equal to 0. And we are replacing this gamma by m with 2b, and that b is the damping factor. 2b for a convenience of writing equation solution for this equation of motion. So that's why we are writing it as a 2b. That 2b, that b is the damping factor here. And this k by m, the square of the natural frequency, that is omega square. So we can replace k by m with the omega square, the square of natural frequency. And here the gamma by m with 2b. That b is known as damping factor here. So then that equation becomes d square x by dt square plus 2b into dx by dt plus omega square x equal to 0, where 2b equal to gamma by m and omega square equal to k by m. Now we have to solve this equation, but in the present discussion, we are not analyzing the total solution of this equation. Just we will show the final equation, and that by using that final equation, we are discussing different cases exist in the damped oscillations here. Okay, so now here this is the equation of motion, final equation of motion, and the solution can be written as a e power alpha t. So the solution of this equation we can write it as a e power alpha t. So the solution we can write it as a x equal to a e power alpha t, where a and alpha are constants. So if you substitute this value in the above equation, that means you have to find out dx by dt, you find out d square x by dt square, and you substitute this um, x value here and dx by dt here and d square by dt square, and simplify, and finally we are getting the solution. So that solution I am writing here, and then, in the present concept there no need to analyze the complete solution for you. So that's why I am writing this solution here. And what is the x naught here? The extreme position of this oscillator, that means the maximum amplitude what we are getting, that is this one. For suppose if you are taking the damped oscillators here, first maximum, then after that amplitude decreasing. Okay, so now this is the extreme position we are considered as a x naught. Okay, so this is the extreme position is the x naught. And b, you all know damping factor, and omega is the natural frequency. So all the components in this are well known to you. Yeah. Now we will discuss three different cases here. One case is b square is less greater than omega square. One case is b square greater than omega square. And next case is b square equal to omega square. Case 2 is b square equal to omega square. And third case is b square less than omega square. We know b is the damping factor, omega is the natural frequency. In this case, b square greater than omega square means damping is very high. In this case, damping is low. And in this case, it is moderate. Now, I will show the animation. You can get clarity about how these cases are can be analyzed by using this animation picture. See this one here. Now the natural frequency we put it as 1 H, and damping factor is 0.03. See in this case, so what will happen, we'll check here. Now the red color is the damping factor here and blue is the actual amplitude here. This amplitude decreases without making any oscillations. See here. Without making any oscillations, the amplitude decreases. So if the b square greater than omega square, the amplitude of the oscillator is decreased with time without making any oscillations. This kind of situation is called over damped. The situation is known as a over damped here. And the second case is what is the second case? B square equal to omega square. In that case, we will take an example of frequency here 2 and damping is 0.05. I am not knowing exact figures here, just we will analyze. That is B square equal to omega square. I will put frequency here and 2H and damping factor is 0.05. But here you observe here, keep in mind here, when start from here, after 3 cells, it becomes 0. The amplitude becomes 0. Now the second case I will show the frequency is increased to 2 and damping factor increased to 0.95. What will happen? We will see here. Start here. Now the amplitude decreases here. So in this case also what happened here? Without making oscillations only, the amplitude decrease here. So and it becomes almost 0 after 2 cells only. That means in the previous case it takes 3 cells. Now in this case only after 2 cells automatically the amplitude becomes 0 without making oscillations. That means when compared with the case 1, in the second case the amplitude decreases very fast. This one is known as critical damping. So if B square greater than omega square, the amplitude decreases with time without making oscillations. That is called overdamp. In the second case, B square equal to omega square, the amplitude decreases with time without making oscillations, but faster than the previous case. So this one is known as critical damping. This one is known as a critical damping. And third one, what third one? B square less than omega square. Mean damping is very low. For example, I will take damping is very less here. Okay. So I will take damping point. Then what will happen? See here. Here it is making oscillations. But amplitude of oscillations are decreasing here. So in the first two cases, the amplitude varies without making oscillations. But in the third case, there is presence of oscillation, and amplitude is decreasing continuously with the time. After certain time interval, it becomes 0 also. So the third case is known as underdamped. Third case is called underdamped. The first case is overdamped. Second case is critical damp. Third case is underdamped. Each damping system will have its own applications. I will show this oscillations in the another animation. You see here the three cases I will show here. So these are the three cases here, and this is the undamped case. That is a free oscillation, the first one. If you see here, in this case, the oscillations are continuing for a long time with same amplitude. But in this over damped, it is coming slowly, see here. But in this case, it is coming fast. So in the first case, it is coming slowly and coming to the rest. But second case, if you say critical damping, say amplitude is coming to the rest very fast here. So the object is coming to rest very fast. But in this, it is coming slowly. So this is called over damped. This is called critical damped. And here also amplitude decreases. But in this case, there is no change in the amplitude. So this is the free oscillation case. We can analyze the things like this. So now we are going to discuss about what are the different applications because of this damping phenomenon. So now B square greater than omega square over damped. In that the amplitude decreases with time without making oscillations, but the process occurs slowly. So this kind of phenomena we are using in the door closures. So automatic door closing mechanism, there what kind of damping occurs here? Over damped here. Second one is the critical damping here, B square equal to omega square. In this case, the amplitude decreases with the time faster than the over. And this kind of Critical damping we are observing in case of shock absorbers. What shock absorbers we are using for bike or car? There, we are using this kind. And third one we have observed, that is under damping. In this case, the amplitude continuously decreases, but here oscillations are occurs. After certain time interval, it comes to the rest. So these are the three different cases of damped oscillations here. Next, we are going to discuss about forced oscillations. So in this next lecture, we are going to discuss about forced oscillations. Till the time, thank you.